mentioned, my name is Eric Johnson. I'm a Firmware Solutions Engineer at Memfault, and today I'll be talking about why Coredumps are great, what they include, how to use them of your embedded device workflow when you're solving problems. A little bit about myself. I joined Memfault because I was really excited to help build tools that I always wanted when I was working at device companies like Walgreens Health, Athos Security Brands, and Lexmark throughout my career. I've been working with Zephyr now for several years. I first started using it in 2018 and have just kind of been contributing bug fixes throughout all the different places that I've worked. And some places where you can find my thoughts and content, check out our interrupt blog. We have a lot of different types of content, not specific to Memfault, really covering everything in embedded systems development. So a quick overview of what we'll be talking today. I'll first start off going over what is a Coredump, what is contained within it. And then I'll move on to how Coredumps fit within Zephyr. And then I will next do a short demo of how to collect a Coredump with Zephyr, how to process it using some of the accompanying scripts, and how GDB Python extensions work. Next, I'll show some features of Memfault and Coredumps, and then top that off with a look into a sample Coredump in our web application. So first, I have a quick poll, really just to get an understanding of how familiar everyone is with Coredumps themselves. And so this question is, do you use Coredumps to debug your crashes that you receive when you've got devices out in the field or if they're at your desk? I'll give this maybe 10, 15 more seconds just to get everyone's answers in. Oh, a few last minute answers. Awesome. Well, thank you everybody for answering that question. And it looks like we have quite a good split. It's great to see that some people are using Coredumps regularly, and kind of what I would expect is that, and I've certainly seen this at previous places I've worked, is that you know what a Coredump is, but it's hard to work them into your normal workflow. And that is one thing that Memfault helps with. So now that we've kind of set a background for everyone's experience with Coredumps, let's jump into what happens when you've got a device deployed in the field. You've probably ironed out most of the kinks. It's away from your desk for the first time. You've probably got some sort of logging subsystem in place. Zephyr provides a really full-featured logging subsystem, which is awesome, really saves you a lot of time in development with that sort of feature. But we've all hit this case where we have a noisy log that really just blows through any of the storage that we've allocated for logging, or just hides and masks other logs that are coming through the systems. So logging is great for cases you have the device right next to you, or you're able to stream this data off the device, but it can be really hard to use in postmortem analysis. There's a lot of things you have to sift through. It's very unstructured. So it does totally have its place, but it is really hard to debug these problems that you can't replicate at your desk. Maybe you're a firmware engineer and you get a service report in, and service report contains your logging here, but it's really hard to know where to begin and how to replicate this issue. Zephyr also provides a really nice kind of summary panic logging feature. And this gives you the idea of, what was the fault that occurred, at least at a high level overview. It shows the contents of the registers when this happens. So it's great for initial diagnosis. But again, we really only have one frame of where the fault happened. And there's a lot of symbol decoding that we have to do here. We just have the raw PC address. So still a lot of work on your end to try and begin to figure out where an error happened here. This is where Coredumps come in. Coredumps are really amazing because they give us a backtrace. We can gather a backtrace of where the fault occurred and what steps our code had taken before leading up to the fault. Coredumps are non-invasive. They're only going to run when there's either a software assertion or a fault handler runs. So that's great because it allows your application's normal runtime behavior to be completely unaffected. Whereas logging, that can interrupt things because there's a background thread being used to periodically write logs into a circular buffer, or if you're using like log immediate mode, now you're waiting for that printf or log function to complete before the rest of your code can run. So logging does have some downsides compared to Coredumps in that respect. The other really great thing about Coredumps is because they have this structured data, makes them easily extendable, especially using features like GDB's Python extensions, which I will cover later on. So what the heck is even contained in a Coredump? And the real key thing to remember about Coredumps is that they are composed of different regions of memory or RAM. The most important things for us to collect when we hit a fault is the current call stack of the context where the fault occurred, whether that is a thread in your system, whether that occurred in an interrupt handler, the interrupt handler happens to use a separate stack, or if you're running a bare metal application, just the current stack that you have for your application. That is what gives us the ability to unwind and create a backtrace in the Coredump. The next kind of piece of it, important information that we need is our system's kernel, or at least in the system to capture. The kernel gives us information on the state of our threads, and it also can give us pointers to the specific stacks for each of those threads. Other data that we can capture could be data around your communication stack, like a BLE stack. You could capture your sensor data. Maybe that's particularly important for your device. Could be using some sort of FIFO buffer, and you're trying to look into issues that cause crashes when you're processing this FIFO data. Could also capture information on your heap so that you understand how your memory is being managed as your device is running. So leading into this, just before I dive into the Zephyr internals, I'm really curious about what RTOSes you typically use in your firmware or your devices. And I'll just give that another 10, 20 seconds or so. Awesome. Well, thank you everybody for answering this one too. Looks like we have a pretty even split between Zephyr and FreeRTOS, a little bit more FreeRTOS, and then a lot of bare metal, which is always interesting. So great. I'll be focusing on Zephyr today, but a lot of these same principles apply for any of the other RTOSes or even in the bare metal case. In the bare metal case, though, we'll just have a single thread to investigate rather than having to parse kernel information for state on those other threads. So let's dive into the Zephyr internals of their Coredump system. So before we begin, though, I'd like to just explain what causes a Coredump in the place. And there's simple faults or assertions. So faults being hardware controlled, this is very architecture dependent. In the ARM Cortex-M case, which I'll be covering today, there are lots of different faults depending on the specific Cortex-M series that you're using. But in general, you can expect hard faults, which are related to memory access and instruction execution, versus like a usage fault, which is caused by divide by zero or a few other causes. And software assertions are code that we specifically insert throughout our firmware to cause an issue or to cause a fault. And the assertion is there for errors where we cannot recover from this state. So we need to go through a device reboot. So let's start with the Zephyr fault handling case. What happens is when a fault happens, this will trigger a fault exception, which we'll call the fault handler that Zephyr provides. And this fault handler will then begin calling into several other functions, but it essentially bubbles up to this Coredump function at the top right-hand side of my screen. The important thing to take away here is that when you do have a fault, a Coredump triggered by a fault, you will only have the top of your call stack will be the side of the fault, so frame 0 in this case. Whereas in an assertion, it's actually a little bit more complicated. And this is because where we call assert, as you can see down in the bottom left-hand corner of my screen, the macro Zephyr has some provided macros. They all start with _assert. You can either provide a message along with the assertion, or in this case, I'm showing using assert no message. When the assert calls, that pushes one frame onto our stack, and then a second frame is actually pushed through this function assert post action. What assert post action does is it calls kpanic. And again, I'm focusing on the ARM Cortex-M architecture here, but this calls the SVC instruction. And when this handler runs, it will again bubble up into the Zephyr Coredump subsystem, as I'm showing again in the top right-hand corner here. And the key takeaway from this diagram is that in the case of an assert, we will have two frames, or rather, two frames will get pushed onto our call stack, and it's the second frame, frame 1, that contains the site of the assertion. Next, I'm going to talk about what components are there to the Zephyr Coredump subsystem. So we just went over what happens to cause a Coredump, and that is either an assertion occurs or a fault occurs. And this will call into the Zephyr Coredump front end. The front end is responsible for formatting all of the memory regions we use into Zephyr's Coredump format. The front end is responsible for retrieving data from the different data sources that we need. These will be things like Arch-specific regions that contain register data or other data that's specific to your architecture and required to decode the Coredump. We'll also gather the call stack data so that we know the state of each of the threads in our system. The other things that we can collect are device-related data. So I'll go over an example of this in a little bit, but we can use different device tree nodes to capture maybe peripheral memory in our devices. And then finally, we can also capture just different raw memory regions as well. That'll be things like collecting all of BSS or maybe all of the data region in your firmware. Once the front end collects each of these regions, memory regions, it will work with the back end. And the back end is responsible for actually writing the data to the medium that has been configured. And Zephyr provides a few different backends by default. There's a logging backend, which I will demo today. There's also a Flash backend, and then there is the capability to implement your own custom backend through Zephyr. All of this, the majority of this, is configured through kconfigs, And you can see a few of these prefixes or suffixes that are common to the different kconfigs options. It can be helpful if you're trying to search through the Zephyr code base just to figure out which kconfigs are important for your device. So as I mentioned before, this is an example of a device region. And what we're doing here is we're using device tree to define a memory region that the Zephyr Coredump subsystem will automatically collect when a Coredump occurs. And the example that I have here is we're collecting a region that I've called Coredump GPIO. And if we look at the address, the starting address in the memory regions property, you can see that it starts at 4000, 4000 and has a length of 1000 hex. So this memory region, if you were to look this up, this corresponds to the GPIO 0 block in the QEMU Cortex M3 target that Zephyr provides. The other important thing to note in this example is the Coredump type. There are two different types of device regions that we can collect. In this case, I'm collecting the simpler memcopy type. And what this means is this memory region is memory mapped. So we can use a simple memcopy call to collect that data for our Coredump. There's a different type called a callback type. And in this case, this allows you to collect data from non-memory mapped regions. Maybe you have a hardware FIFO where in order to iterate through the data, you have to perform subsequent reads at the same memory address each time. That would be a use of the callback type. The screenshot that I have here is an example of using the Zephyr logging backend for our Coredump. And you can see that we get the standard panic output that I was showing before and discussed. And then following this, we have our actual Coredump data. And so it's formatted as text. And this requires a specific step to convert into our Coredump binary, which I will be covering later on in our webinar. So before I get to the demo, just want to go over a few of the host tools that are required to process and load a Coredump. The first step, if you're using the logging output, is to use the logging converter script provided by Zephyr. What this does is it takes that text output that we just saw in the previous screenshot and turns it into binary data that the Zephyr GDB server can read. The next component are the different parsers that Zephyr provides. There is an ELF parser, which reads in different memory regions that are defined in that ELF file or the symbol file. This is needed to desymbolicate the raw addresses that we have in our Coredump data with, say, the function names or variable names as we're stepping through and looking and investigating our Coredump. The GDB server is there to read this Coredump data, and it implements the GDB remote protocol. This is a protocol that GDB defines and essentially allows GDB to the GDB client to access the data that we've saved in our Coredump file. The GDB server also contains some Arch-specific code, and this is needed so because of the differing register sets and maybe peripherals that differ from architecture to architecture. So now that we have an understanding of the host tools required to process and look at Coredumps, I want to cover how you can extend these capabilities through Python extensions. This is a really great feature of GDB, and it's very flexible, especially it's very nice to be able to script this using Python. A couple things that I want to highlight here is that you should be using the -pi suffix of the Zephyr toolchain when you're using the GDB client. This version of it includes the Python extension support. If you use the NoPy version, which is the default, you'll get an error message that it can't support the extension features. When you're setting up your own environment, I always work with an isolated Python environment using VN for a virtual environment. This is very helpful because it avoids stomping over maybe some system-specific Python packages you have, or maybe you have a Python project you're working on yourself and you have specific dependency versions required for that. By using an isolated environment, you keep those two things separate from each other, and you're free to experiment and install whatever packages you need for your GDB setup. The other recommendation is that we have written a small package called GDB bundle, and this helps manage your Python extensions that you're writing for GDB. It's a really nice feature, and I'll kind of show how this is tied together with GDB in just a little bit. So now that we've gone over what a Coredump is, how it operates within Zephyr's RTOS system, let's go ahead and take a look at a demo. So what I have here in my first window is a Zephyr environment that I've set up. You can see that I am using a virtual environment here. The directory is called venv. And what I'm going to do is run a sample application that I built. It is using the QEMU Cortex M3 target that Zephyr provides. So I'm going to go ahead and run this with westbuild-t. And we've got our application running. I've included a shell component to this. And in this demo, I have a sensor that I'm running and talking to in my QEMU app. So I'm going to go ahead and run and enable my sensor here. And I knew this was going to cause a fault, but this is just an example of the output that you get when a fault occurs in Zephyr. So if we scroll up to the top here, there's quite a bit in output. Again, we see that panic message that Zephyr provides. So we have a very top level view of what might have happened. We have some logging messages before there, but then the guts of our Coredump are below this. So I've already saved this output into a text file, and I'm just going to exit the emulator here, clear my screen. The next thing I'm going to do is we've got our Coredump.log saved. This has the contents that we just saw when we were running our program. And I'm going to run Zephyr's serial log parsing script to convert this into a binary file here. So this script is, again, located within Zephyr itself, which is great. If you've got a Zephyr environment set up, no extra downloading required. All you have to do is run this script. The first argument is that logging file that we just created. And the second argument is the output file that we will create once this script runs. I'm going to go ahead and run this. And you can see that it created our output file, coredump.bin, and wrote about 20K of bytes to that. Next, I'm going to start up the GDB server that Zephyr provides. And again, we will just take a look at this command that I'm running. So we're using the GDB server Python script. The first argument is going to be our symbol file, which by default, Zephyr will name zephyr.elf. And then we're using that coredump.bin file that we just created in the previous step. Now, once this runs, it is waiting for a GDB client to connect to it. And in another window, I'm going to connect to our GDB server. And this command is a little bit long, but what I'm doing is I'm using the GDB client provided with the Zephyr SDK for the ARM toolchain in this case, because I'm using a Cortex-M device. The important thing, again, to note is that I'm using the -pi variant here. This will include the Python scripting capabilities. The option that I'm using here, this command option, what this does is it is loading a GDB init script before we complete starting up the GDB client. The last argument that I have here is, again, our symbol file. Just to take a peek at what the GDB init script is like, I've got this open in a Vim window here. And we can see what this is doing is it's using different GDB client commands to essentially initialize our GDB session. As I mentioned before, really encouraged the use of GDB bundle. It has saved me a ton of time and effort to create different extensions, especially the ones that I did for this demo. The GDB bundle requires just a small amount of startup script to run. And what it's doing is it's setting up different Python paths so that GDB bundle can automatically find different extensions and load them into our GDB client. The last step here is that we are connecting to the GDB server that we have started in a different process. And by default, the Zephyr script starts the server up at the port 1234 on localhost. So now that we've kind of walked through that, I'm going to go ahead and run our GDB client. And great, we can see that GDB has paused us at this function calculate transformed reading. And this is in fact where the fault that we hit runs. We can use GDB commands that we know and love, like backtrace here, to see what we are doing in our code prior to calling that function where the fault occurred. And then just as another quick demo, we have a few different GDB extensions installed here. And so one of these is called Zephyr threads. This will use those different memory regions that we collected, particularly the kernel memory regions, to give the state of the different threads in our system. You can see that we have our processing thread that was running, our system work queue, we have a shell thread, logging thread. Really gives you a great idea of what else was going on in the system when the fault occurred. And then finally, to demonstrate that device region that we collected as part of the GPIO block of our QEMU device, I have created this this GPIO command, that is used to print out the state of our GPIO peripheral. And this can be really useful, I've found, when I have some hardware that is connected to my device, maybe a SPI peripheral, or in this case, I'm using GPIO pins. But this is really useful for parsing through those peripherals where they might be in an unexpected state, something that you weren't planning for when you wrote your code. Maybe an interrupt is enabled when it shouldn't be. I've definitely run into those cases where it's just really useful to know exactly what state all of your peripherals are in when the fault happens. So that's the conclusion of our Zephyr demo. I'm going to jump back to our presentation now. And now we'll move into what features and additional capabilities Memfault brings to Coredumps. So this is what a Coredump looks like in the Memfault web app. And really what we're doing is we provide a lot of capabilities in terms of processing your RTOS's state, the state of the different threads that are running, all stack of the threads will provide, we can capture information regarding local variables and registers in the thread that caused the fault. And then we also can capture different memory regions that you define using the Memfault SDK. This is really great for capturing, say, your heap in your system to understand what the heap was like when the fault occurred. And then finally, we do a lot of tedious and difficult work that you may encounter if you are processing Coredumps locally. One of the great things that we do is we take a look at all the Coredumps that are sent, and we try to group them together into different, what we call issues. So each Coredump belongs to a specific issue. And this way we can group these Coredumps together so that you're not having to manually determine this fault was caused by issue Y, whereas this fault was caused by issue X. The other thing that we're doing is, you may have noticed before that as we're loading up GDB, we always needed both the Coredump binary and our symbol file. We take the hard work of always having to pair those two together and do that for you through built-in build IDs and other features. This is just a summary of kind of what I've gone over with Memfault. And a few other things I'll touch on is that we provide a web app so that you don't need a full development environment set up in order to start looking at issues. So it's really great for team members that are working on other things and maybe still want to understand what the problem was and analyze it with you. And as I mentioned, we use build IDs and software versions within your symbol file to help match those core dumps that we receive and collect and match everything together. So with that overview of Memfault, I'm going to go ahead and jump into an example that we've collected as part of some demo data. And what we're looking at here is the issues view in a demo project on Memfault. And especially great because we occurred, where it happened, and why it happened. And so let's take a look at this mem that we have here. So what we're looking at is the issue view within Memfault. We've got the state of all the threads in our system that were running when the fault occurred. And this is an example collected with Zephyr. We can see that our accelerometer work queue was the site of where the fault occurred. And we have done extra processing to determine that it was a stack overflow that caused this. This matches with the Memfault classification that we've done. We can see that this occurred at the compute FFT function here. We are also matching all of the addresses back to your symbol file, so you'll know exactly where in your code this fault happened. We also will do some work to calculate the high water mark on each of your threads. And this is a really great feature for trying to understand if one thread has too much memory allocated to it or too little. In this case, we hit a stack overflow, so we might want to look at, is this normal memory usage, or was our thread behaving badly and it just maybe infinitely recursed as was in this case. We can also take a look at the state of the other threads in our system and see that, check how their stack usage is as well. And this kind of tells us like, oh, maybe we could divvy up some memory from this net management thread and give it over to our accelerometer work queue. We will do a lot of hard work that is decoding the different fault registers that ARM provides so that we can tell you exactly what address this memory fault happened at and what type of memory fault really was this. And in this case, we were accessing memory out of bounds. We'll collect information on the register and local variables at different points in the stack. So we're doing a lot of stack unwinding work that I found very tedious and very difficult in my previous roles. We'll also capture those different memory regions that I referred to. In this case, we can search and look through all these symbols that we've collected, and we could take a look at and dive into the Zephyr kernel itself. And then finally, one other last pane that I'll highlight here is our memory viewer. And this allows us to check out specific regions in memory that we've collected. And we can take a look at these regions to see, just at a very raw level, what were the bytes included here and what did things look at. I recently ran into this being a very useful feature working with a customer where they had a stack overflow that essentially corrupted the entire stack region that we had. It was very obvious that this happened because all of the data in our region looked exactly like text. So we were able to very quickly narrow this down to a string operation that had corrupted their stack. The last thing that I'll highlight is just all of the kind of metadata that we're creating from these core dumps that we've captured. We are calculating how many instances of this issue have we seen, how many different devices it's hit, which cohorts, which is how we split up your fleet, which cohorts this is occurring in, on what software versions, and on what hardware this fault happens at. So just as a very brief summary of why all this matters, I really think Coredumps are quite a game-changing tool. Once you add them into your workflow, it just provides a much more complete picture than logging can. And it allows you to capture this information in a post-mortem fashion without affecting the runtime behavior of their code. And it can be done remotely as well. I highly, highly recommend to use Coredumps early, both early as in your development cycle, get them in place, get your workflows up and running as early as possible, because those are often the most annoying bugs to work through. Like if you're doing board bring up and you're introducing a new peripheral, it can be really aggravating to work through those issues. So getting a Coredump system in place right away is especially beneficial. And then often, as in, get this into your regular workflow, because the more data you collect, the more Coredumps you collect, the faster you'll be able to solve and identify issues. So thank you for attending today. We'll be doing Q&A shortly after this, but you can find me on LinkedIn or at GitHub. And then also I encourage you to check out Interrupt. As I said before, it's a really great resource for all sorts of debugging and embedded problems. And if you're particularly interested in Coredumps or helping device companies solve their problems faster and build tools around that, we are hiring. So please check out our website for the career postings. Thanks.